Today, we're going behind the scenes to look at how one of the world's most trusted names in hand tools, Bahco, manufactures its iconic adjustable wrench. The process kicks off with raw steel billets, high-grade chromium vanadium alloy steel to be exact. This isn't your ordinary hardware store metal. CRV steel offers exceptional toughness, outstanding wear resistance, and the ability to handle serious torque without deforming. It's the gold standard for professional hand tools. Those billets go into a powerful drop forge press, where intense heat around 1200 degrees Celsius makes the steel malleable. The press then strikes with thousands of pounds of force, shaping the rough wrench body in just a few blows. This forging process aligns the grain structure of the steel, making it significantly stronger than a cast piece ever could be. After forging, the wrench heads through a CNC milling station, where the jaw surfaces, the worm gear channel, and the adjustment slot are precision machined to tolerances measured in hundredths of a millimeter. This tight precision is exactly what gives a Bahco wrench that smooth, non-slip grip on a fastener. The worm gear, that little knurled wheel you turn with your thumb, is manufactured separately and pressed in with a precision fit. Then the entire assembly goes through heat treatment and surface hardening to extend the life of those critical jaw surfaces. Finally, a dip in a chrome plating bath gives the wrench its signature polished look, while adding a layer of corrosion resistance. Each unit is inspected, stamped with its size specification, and packaged. The machine you're looking at is the G550T, a high-performance 5-axis CNC machining center that has earned a serious reputation in precision manufacturing shops around the world. It combines a rigid cast-iron column structure with high-speed linear guides, giving it the stability needed to maintain accuracy even during aggressive cutting passes. The G550T's spindle is the heart of this machine, capable of reaching speeds of up to 12,000 RPM with a powerful 30-kilowatt motor driving it. That means it can comfortably handle everything from high-speed aluminum roughing to demanding stainless steel finishing cuts without breaking a sweat. We start with a solid block of 1440 alloy steel, clamped securely into the machine's hydraulic vise. The operator loads the CNC program, a digital blueprint that maps every single tool path, cutting depth, and feed rate. There's no guessing here. Everything is calculated to the micron. Watch as the roughing end mill begins removing large amounts of material in sweeping passes, giving the part its rough outer profile. Coolant floods the cutting zone continuously, carrying away chips and keeping temperatures under control. Then, the machine automatically changes to a smaller ball-nosed end mill for the fine finish work, contouring curves and blending surfaces to a near-mirror quality. The finished part slides out of the vise dimensionally perfect, ready for quality inspection with calipers and a coordinate measuring machine. This is modern manufacturing at its finest. Now, this is where precision meets power. What you're looking at is the Holroyd EX Series CNC rotor milling machine. And folks, this isn't your grandfather's milling setup. This machine is recognized worldwide for blazing speed, extraordinary accuracy, and build quality that simply sets the standard for the entire industry. The EX Series is purpose-built for one job: cutting rotor and screw profiles with absolute perfection. We're talking workpieces up to 850 millimeters, that's 33 inches in diameter. For context, that's roughly the width of a grown man's shoulders, and this machine cuts through it like it's nothing. Every pass of that cutting head is computer-controlled down to the micron. No guesswork, no human error, just pure, repeatable precision. Turn after turn, piece after piece. Companies building compressors, turbines, and industrial screw assemblies trust Holroyd because downtime isn't an option at that level. And watching this machine work, it's almost meditative. Today, we're going to walk through the fascinating, remarkably precise process of how seamless steel pipe's made. Now, you might wonder, why seamless? Seamless pipes are a single, continuous piece of steel, no joints, no welds, no weak spots. In high-pressure, high-temperature environments, that is safe. The process begins with a solid cylindrical steel billet, a short, thick rod of high-quality carbon or alloy steel, typically cut to precise lengths by a circular saw. These billets are first inspected and then loaded into a rotary hearth furnace, where they're brought up to temperatures of around 1250 to 1300 degrees Celsius. At that heat, the steel glows a brilliant orange-white and becomes workable enough for what comes next. This is where the magic happens, the Mannesmann piercing process. The red-hot billet is fed into a piercing mill, where two barrel-shaped rolls are set at opposing angles to the billet's axis. As they rotate, they don't just spin the billet, they create a powerful helical rolling action that causes immense internal stress inside the steel. A pointed mandrel, a long hardened steel rod, is positioned right at the center of that stress point, and with remarkable efficiency, it punches through the billet, forming a hollow tube called a bloom or shell. That hot hollow shell then moves to a plug mill or a continuous mandrel mill, where a long internal mandrel rod is inserted and the pipe is progressively elongated and reduced in wall thickness through multiple rolling passes. The outer diameter is controlled by external rolls, the wall thickness by the mandrel, working in perfect coordination. After rolling, the pipe enters a reeling mill and a sizing mill that true up the outer diameter to final specification and improve the pipe's roundness. From there, it goes to a straightening machine, because even the best rolled pipe picks up a slight bow during processing, and then into a cooling bed, where it slowly returns to room temperature. Before a single pipe leaves this facility, it faces rigorous non-destructive testing. Ultrasonic inspection scans the pipe wall for internal flaws. Electromagnetic testing checks for surface cracks, and a hydrostatic pressure test floods the pipe with water at pressures far exceeding its rated working pressure. Only after passing all of these tests does the pipe receive its end facing, threading if required, and inspection markings. Have you ever wondered what actually goes into making golf balls? Weiss Golf, a German brand that's been shaking up the market with premium balls at accessible prices, gives us a fascinating look. Every Weiss golf ball starts at its core, a small, resilient sphere of synthetic rubber compound that's mixed, formed, and vulcanized under heat and pressure to precise hardness specifications. The core's compression rating directly affects the ball's feel and energy transfer. That core gets wrapped in one or more mantle layers, injection-molded shells of ionomer or urethane blends, which control spin separation between driver shots and short game shots. Then the cover is molded around the entire assembly. Weiss uses a cast urethane cover process for their premium lines, giving that soft, responsive feel around the greens. Finally, paint application, stamping, and a clear coat finish bring the ball to life. Every single ball is weighed, measured, and symmetry checked before it earns the right to go into that iconic Weiss sleeve.